So we're starting in chapter 5.3, which is all about growth and decay. Growth and decay models. And I first wanted to speak a little bit about exponential growth and exponential decay. Exponential growth is generally given by the equation, and we can use a generic here. We can say A is equal to A0 e to the power RT. Exponential growth and decay, usually given by this model here. Where A0 is the initial amount or quantity. R is the rate. And it could be negative or positive depending on if it's decaying. So positive for growth, negative for decay. And T is the time. Now, exponential growth, as a rule, they tend to start off really slowly and climb really fast. So in a short period of time, the number goes right up pretty fast. For example, let's take the flu, the spreading of the flu virus. And this is just an example I made up, okay? It's flu virus spreading. So let's say at day 0, people with flu. And at day 0, 2 people have the flu. At day 1, it's double that amount, 4 people have the flu. At day 2, 8 people have the flu. Day 3, 16 people have got the flu. Day 4, 32 people have the flu. And you can see the growth rate happening here, that ratio, that constant ratio. Constant ratio representing the base of the model. That constant ratio is equal to 2. 16 divided 8 divided by 4, 16 divided by 2, and 32 divided by 16, that ratio. So our model here would be population is population times 2 to some time, okay? Some time. And we can put that time as x. So I want to show you what happens here. So at day 0, 2 people had the flu. So this model is 2 times 2 to the power x. Now, let's graph that model and look at it. Y equals to 2 times 2 to the power x. And if we graph it, we see this model that climbs. Now what I want to do is increase the axis, the window for this. So I'm going to put this back at -10. Okay, we don't need to see anything other than -5. -5 is good. Let's put the maximum number of days at, say, 100 days. And let's put the maximum at, say, 50,000. I might be doing too much there. Let me look at the graph. Okay, so you can see what's happening here. At day 20, the virus has spread to 2,997,152 people. At day 5, 64. At day 10, 2048. At day 15, 65,000. Okay, so our graph kind of goes out the range for that. I mean, you would have to fix the window to perhaps 150,000 to get an in-depth picture. And let's calculate, say, day second, calculate the value at, say, day 15. And now you can see on the graph at day 15, 65,500 people have the flu. I'm just going to capture this and put it into our graph so you can see it. Because I wanted to show you how exponential models work in terms of a practical application of it. Okay, you see the steep climb. It starts off really, really slow, as you can see from these numbers here. And then it does that steep climb. Now, I wanted to also explain the difference between an exponential growth model and a logistic model. So the exponential growth is for, or it represents unlimited, represents unlimited growth, such as population, money, bacteria, etc. Okay? A logistic growth model is a form of the exponential growth, but after a while, that J-shaped, remember this is J-shaped, the graph levels off at a certain point. In other words, the graph is not unlimited. Unlimited versus leveling off. That's what I wanted to point out to you as the difference, the big difference between exponential and logistic growth, unlimited graph. So I wanted to go ahead and look at some of the problems from the homework with you. Let me give me a second to access it and bring it in here. Let's see if I can do that. Insert, file printout. What are we looking for? This is 2233. This is the homework problems. I need can't find the stupid thing. Where did I put it? 5.3 handout, insert. Let's see if this works. Yay, it works. Okay, so let's put in our problems here so we can follow. The first question here is asking us to use a graphing calculator to graph this model, and it's giving us the windows that we need to set. And it's now this is a logistic growth model, and it can be any one of these. So we want to go ahead and put it in our calculator and see exactly which one of these graphs is represented by it. So let's put this in our calculator. Be very careful putting this in. Okay, so I'm going to use the fraction bar, type in my numbers over 1 plus 2999 e to the power negative 0.6 t. So in place of t, we're going to use x. Now, I want to go ahead and fix the window given what they gave us here. This should be 0. Then they told us the maximum x value is 60. 0 to 3000. And graph it. And you can see that nice S-shaped curve for the logistic model. Notice instead of a J, now it comes out to be a nice S-shaped chord graph. We're going to go ahead and copy this and paste, put it into the notes. I think I should go put it in at the bottom here, right? That might be easier for us, yeah, because we can blow it up here. So this is question 1. And I think the graph represented by that looks like it's it goes all the way up to 3000. So it's graph C would be the correct graph. The next question, question 2, is asking us to find the value of t for which the logistic model given below equals to m over 2. So they're asking us to set m1 plus c e minus k m t equal to m over 2 and solve the equation. This is what they're asking us to do here. So rewriting here, we're going to, if we go ahead and cross here, we're going to have 2 is equal to, bring the 2 up m times 1 plus c e to the power negative kmt divided by m. And that allows us to cancel out the m. So 2 is equal to 1 plus c e minus kmt. Now we have to calculate t here. Moving along here, so we can take away 1 from both sides. So ce to the power minus kmt is equal to 1 if we take away 1 from both sides. So e to the power minus kmt is equal to 1 over c. Now, taking logarithms on both sides, e minus kmt is equal to logarithm 1 over c. Using the power rule for logarithms, we can bring that kmt to the front. So minus kmt ln e is equal to, and then this is a quotient which we can split up ln minus ln c, ln1 minus ln c. We know that ln e is equal to 1. So minus kmt is equal to ln1 minus ln c. Now, ln1 is equal, I forgot to mention that ln1 is equal to 0. We don't need that in there. So this is minus ln c. So t is equal to ln c over km. ln c over km. A bit of calculation to get that, but you can figure it out. The next question: in a nuclear disaster, there are multiple dangerous radioactive isotopes. It's 90.2% of a particular isotope emitted during the disaster was present 4 years after the disaster. Find the continuous compound rate of decay. So I'm going to have to do question 3 on the bottom here. Okay. This involves a little bit of work. First, we're going to use, this is, let's use the P, doesn't matter what we're, P0 e to the power RT, the general model. And we're told that the population after 4 days, let's write that out, after 4 days is P is equal to 90.2%, which we have to convert to a decimal, so 0.092. So this is equal to 902 of the original amount. So we're going to go back to our model now and substitute 0.0902 P0 equals to P0 e to the power 4 times R. Remember, T is equal to 4 days. Okay. So P0 would cancel out here. I don't want to mess this up too much. Let me do it in a second step so you can see it canceling out. So 0.902 P0 is equal to P0 e to the power 4r, and then p0 would cancel out if you divide both sides by p0. So we have 0.902 is equal to e to the power 4r. Take logarithms on both sides, so ln 0.902 is equal to ln e to the power 4r. Then use the power rule to bring 4r to the front. And that gives us 4r ln e. Ln e is 1. So dividing both sides by 4, r is equal to ln 0.902 divided by 4. Round to 6 decimal places. So we're going to put that into a calculator. Natural log 0.902 divided by 4. So to 6 decimal places, to 6 decimal places, 0.25 7851897. That's the continuous compound rate of decay. Now when you write that in, you don't put in a negative sign. The negative sign tells you it's decay. But when you write the answer, you put 0.025785. Don't put in a negative sign. We know this is decaying at that rate. Okay, you're going to get a negative answer. But the actual rate is 2.5785 decaying, which is a negative growth rate. And finally, question 4. The amount of carbon-14 present in animal bones is given by this exponential decay equation. A bone has lost 24% of its carbon-14. How old is the bone? So we want to go ahead and say that P is now equal to, if it's lost 24%, 76% of P0 is left. Okay, 100 minus 24 is equal to 76%. As a decimal, this is 0.76 PO. Same process here, so we would go ahead now into our equation that we're given. P0 PT is equal to P0 e to the power negative 0.00012t, and substitute for P and P0, substitute for P0, 0.76 P0 is equal to P0 e to the power negative 0.00012t. Notice that the p's are going to cancel out, so we get 0.76 is equal to e to the power negative 0.00012t. Take logarithms on both sides. Use the power rule to bring that to the front. Negative 0.00012t ln e, which is 1. So t is equal to ln 70.71 divided by negative 0.00012. Calculator, round to the nearest whole number, integer. So logarithm 0.72 divided by negative 0.00012. I'm sorry, that's 0.76. Logarithm 0.76 divided by negative 0.00012. To give 2287 years old. So this is 2287 years. This is 0.76, sorry, 0.76. Okay. To the nearest integer, 2287